First, let me add to the congratulations for both Shimon and Eliezer. I've known them both for about 30 years, and it's always been an incredible pleasure to be in their company for many reasons, not just for physics reasons, but also for other reasons, cultural reasons, social reasons, and so it's particularly nice for me to be here. And also, I have taken the opportunity of being here to travel around the country visiting numerous relatives, so it's been a delight. I've got it. Is that another one?
It's on.
How many do I need? I need two.
Yes.
Ah, okay. So thank you both. So I'm going to give a talk about work I've done over the years recently in just basically trying to find out as much as possible about the properties of graviton scattering, four-graviton scattering, a very small section of the M-theory structure, but try out and find out as much as possible about it using the kinds of symmetries that we're familiar with or we expect to be contained within string theory or M-theory or whatever. The point being that one might be able to discover a great deal in the context of a theory which has a huge amount of supersymmetry, which raises problems in using traditional supersymmetric methods for discovering properties of the action or the amplitude. So the basic problem with so much supersymmetry is there's no off-shell supersymmetric formulation, so it's very difficult to come across certain kinds of non-renormalization theorems or certain ways of counting, of deciding which processes are forbidden and which are possible. So what I will talk about will essentially be in three stages. The first stage will be to concentrate on certain rather specific types of terms in the derivative expansion of the amplitude. And if one talks about certain rather specific terms, then one can make exact statements which contain a lot of detailed information, both perturbative and non-perturbative. These are terms which in some sense are protected. And for example, I'll be talking a lot about the type 2b theory, in which there is the well-known SL2Z duality symmetry, which constrains the amplitude and the action in a very profound way, as we all know. In order to determine some of what I'm going to talk about, I'm going to appeal to the duality between 11-dimensional supergravity and string theory, 11-dimensional supergravity on a 2 torus, and string theory in 9 dimensions or in 10 dimensions. And but I'm going to use quantum properties of supergravity in order to make the discussion, as you'll see. And then conversely, by insisting that supergravity, some appropriate quantum version of supergravity, should correspond to string theory, one may be able to determine certain properties of supergravity using that constraint. And then finally, I'm going to talk about whether one can make statements about n equals 8 supergravity itself, n equals 8 being, of course, the maximal supergravity in 4 dimensions. And there's an issue about whether or not it could conceivably be finite that's been discussed by, in particular, people associated with Zvi Bern and his collaborators, and more recently us. And let me just say right now, I have no idea whether it's finite or not, but there are some indications that it might be, and if it is, then maybe what I'm going to say has some relevance to it. But what I'll end up by saying is that in any case, that may not be a sensible question, because it seems very unlikely that n equals 8 supergravity, whether it's finite or not, can be decoupled from string theory. In other words, whether or not the perturbation terms are finite one by one, it's very unlikely that the whole structure, the perturbation theory makes sense by itself, ignoring all the other states of string theory. So, yes?
We're going to be in 4 dimensions, right?
We're going to start in higher. We're going to end up in, when I said n equals 8, I meant
the goal is 4 dimensions eventually?
The n equals 8 statement was meant to be a 4-dimensional statement.
Yeah. Just one question. Aren't there infrared divergences in 4 dimensions?
Oh, so when I say finite, I'm sorry, I mean ultraviolet finite.
Right.
And there are infrared divergences, I'm assuming we know how to deal with.
Well defined this matrix that one can calculate.
Yeah, for gravitation, for graviton.
No, yeah. It's the same kind of infrared divergences for gravity in 4 dimensions as electrodynamics.
Oh, okay, yeah, sorry. We know what to do with them, as we do in electrodynamics.
Not really.
It's not like having a conformally invariant theory, like
no, that's correct. But
right.
We have to do Bach notes in
Yeah. But it's better than Yang Mills. So I'm going to talk about some very, very small aspect of the effective action of M theory that has to do with R to the 4th terms, because I'm talking about Four-Gravitons, and furthermore linearized curvatures, and there will be coefficients, these E functions, which are functions of the scalar fields. I'm going to take the scalar fields to be constants, basically coupling constants, and there is a whole series of terms in the derivative expansion with infinite numbers of derivatives, with arbitrary numbers of derivatives. So this is a tiny subset of the full action, but we will see that for the lower lying terms, going up to some order, one can determine the properties of these functions exactly, at least for the very lowest lying ones exactly, and for slightly higher ones, they seem to be exact as far as we can see. And these functions E satisfy rather interesting looking equations, Poisson equations, Laplace equations with sources on moduli space, and they have a very rich structure of both perturbative and non-perturbative terms. And there are some rather fascinating patterns involving multiple zeta functions which correspond to other patterns which have been seen in ordinary field theory perturbation expansion. Yeah.
R to the 4th is some particular tensor structure.
I'm sorry, I should have said, whenever I write R to the 4th here, I'm talking a very particular contraction which I'm not going to show you explicitly, but which is implied by what I'm going to say. So I'm going to start by some very elementary observations that all of you should know. Well, all of you who think you're string theorists should know, and those of you who are not string theorists will therefore learn. And the ones who are string theorists will be happy to see things that they are very familiar with. If they're old enough, they may have forgotten them. Namely, I'm going to talk about the data that has to be fitted. So if one wants to talk about the full non-perturbative structure of these terms, it had better be true that one reproduces what is known in string theory, and what is known in string theory is rather limited, known explicitly in great detail, and it comes from tree level and one loop, and actually there are 2-loop calculations, but nobody has analysed the what I'm going to say for the 2-loop case. So the tree level is simply the Virasoro-Shapiro formula. Gabriel's sitting there, I've got to of course say this is the closed string version of Gabriel's original theory, which was the open string theory. And you're all hopefully familiar with this formula. It's just a very trivial expression. The 4-particle amplitude is simply given by an e to the minus q phi, which is the 1 over the coupling constant squared, tree-level coupling. R to the 4th factors out. It's a kinematic factor. It involves 8 derivatives, 4 powers of the curvature. And t is a scalar function of the Manstein invariance, and it's this very simple scalar function here. And if I'm talking about the derivative expansion, what I'm really talking about in terms of amplitude is the expansion in powers of st and u, or alpha prime.
Why did you put 1 over g squared? Just for the action, it takes a 1 over g squared.
Oh, I'm sorry. I changed all these. Yeah, I'm sorry. I forgot to do that. You're right. I think about the action the whole time because I don't really want to talk about the action, because the action is not. I don't decide which action I'm talking about. There are non-local terms. I want to talk about the one-particle reducible action, and then it gets complicated. It's easier to talk about the amplitude, so I changed the transparency, but I forgot to get rid of that. This function t can easily be expanded in powers of st and u, and it gives an infinite series of terms, and let me just flash them up, because I want to illustrate some of the patterns. So this goes on forever. This is a power series in st and u. The first term is simply a neat way of writing the tree-level scattering amplitudes of given by the Einstein-Hilbert action. And then there's an r to the 4th term, which is it's got a coefficient zeta 3 and is a constant. because it multiplies after the fourth, and then there are higher order terms, which are higher derivatives, which have a pattern of zeta functions multiplying rational coefficients. So it's really these patterns of zeta functions times rational coefficients that we want to explain. There are certain terms which are linear in zeta functions, and then you start to develop quadratic terms, and then, of course, higher order terms. So, in a sense, we want to this is the data that we want to embed in our non-perturbative description. One loop, again, can be analysed straightforwardly, but it's actually very complicated to analyse, and there's extremely little known about it up to recently. People have taken the lowest zeroth order term in the past, but they haven't really analysed it further. And the reason for that is it's rather difficult to expand this in powers of S, T, and U. This is an integral over the worldsheet torus of a modular function of the worldsheet and a function of S, T, and U. And it's rather difficult to expand in powers of S, T, and U. What you have to do is integrate products of Green's functions in the torus over the torus, and then you have to integrate over the complex structure of the torus. And that's rather technically complicated. And then there's added complication. You start to get threshold terms, which are difficult to separate from the analytic terms in 10 dimensions. And in fact, what we've done is looked in 9 dimensions by complexifying down a circle, and then you can then you find a large number of coefficients because you can get different powers of the radius r. So these are some of the coefficients. Actually, these are all, I think, incorrect, but the spirit is there. I mean, we know the correct ones, but when I wrote this transparency, we made mistakes. So these are some of the terms that come in at 1 over r. And again, you find a pattern of coefficients which are rational functions times harmonic sums, or products of zeta functions, which reduce to products of zeta functions. It's difficult to extract these terms. Some of them are zero. And in particular, let me point out, as you will see very soon, it's relevant that there is no d to the fourth after the fourth term. It's sort of tricky to see that. I mean, it's very difficult to extract that from the expression, but it's important for what follows. So that's the data that one wants to include, but we want to talk about what is the non-perturbative completion. So now let me talk as if I'm talking about the action, but I'm really thinking of the amplitude. The action is, in principle, an infinite power series in alpha prime with where S with some index indicates the power of alpha prime I'm talking about. So S naught is Einstein-Hilbert action. The answer to the fourth term is order alpha prime cubed relative to the Einstein-Hilbert term. And then there are higher order terms, as I've shown. And some of these have been known for quite a long time now. And these are the ones which have been known about for some time. The Einstein-Hilbert term, of course, the r to the fourth term, and the next term, d to the fourth r to the fourth. And whereas the Einstein-Hilbert term is by itself invariant under SL2Z, so the way I've written these, the factors of e to the phi are simply the ones which come by going from Einstein frame to string frame. SL2Z invariance is easiest to see in Einstein frame. So then, in Einstein frame, you just delete the e to the phi's, and the curvature scalar is by itself invariant under SL2Z in Einstein frame, and then these z functions are meant to be modular functions, and we know what those modular functions are. I'll tell you in a minute one way of getting them, but they are simply Eisenstein series, not a holomorphic Eisenstein series, where the notation, since I've used tau already for the worldsheet torus, omega here is the coupling constant, the string coupling constant, the 2b string coupling constant, where omega 2 is the inverse coupling. So this is a simple Eisenstein series.
Michael,
Yeah.
can I ask a question about this? This is an action that's defined just in order to reproduce the S vector. So
What really I shouldn't...
There's a field redefinition.
Sorry, as I said, I really want to talk about the amplitude. So everything I have to say could have been said directly with the amplitude, then you wouldn't have asked the question.
Okay. So these coefficients you're saying are just referred to certain structures in the
Yeah, and the distinction becomes important actually at some higher order that we're going to talk about, where you start to get non-local terms in the action.
Right.
So these functions Zs have very simple large omega 2 or small coupling expansions, they have two power behave terms, which will be which are the perturbative string theory terms, and then an infinite set of instantonic terms, the instanton terms. And the particular terms that you get depend on the index. So for Z3 halves, is that pointing? Ah, thank you. So there's always a tree level term with a zeta of 2s, so that's a zeta of 3 that we were talking about in the answer to the fourth case. And then there's another term which has a power of omega 2 to the 1 minus s, and then allowing for the factor of e to the phi up front. This always corresponds to an s minus a half loop term, which for r to the fourth is a 1 loop term. So r to the fourth has a tree level term, 1 loop term, and no other perturbative terms. So this indicates that there's a non-renormalization, perturbative non-renormalization to all orders once we know this is the exact function. And then instanton terms. For Z5 halves, there is a tree level term and a 2 loop term, but there's no 1 loop term. That's the fact that I told you about earlier, that d to the fourth r to the fourth doesn't arise at 1 loop in string perturbation theory. So that fits with that particular piece of data. But there is a 2 loop term. Yes?
The things that were cubes of zeta functions in the previous expression, do they arise from?
Well, that's where I'm heading for. Sorry. So this is old stuff, what I'm now talking about. And then I'll come to relatively new stuff, and then I hope at the end I'll come to very new stuff. The defining feature of these z's is that they satisfy a Laplace equation on moduli space with a particular eigenvalue, which is related to the index s. And although the way these were discovered, this just seemed like an accidental fact. Of course, it isn't accidental, and it can be shown to arise as a consequence of supersymmetry, where you, because there's no off-shell superspace way of understanding this, one has to use some clumsy procedure. At least the only procedure we knew about was a clumsy procedure, where you iteratively add a correction term to the action and a correction term to the supersymmetry transformation, and you insist that the corrected action be supersymmetric under the corrected supersymmetries, and then of course you have to ask for closure of the action on the, but for this closes on shell, so it has to close modulo the new equations of motion, and when you apply this, you discover that you do this by a fortuitous choice of particular terms in the action. So S0 here was meant to be, S3 was meant to be R to the fourth action, but of course there are many supersymmetric partners of R to the fourth, and by choosing a particular set of such supersymmetric partners, Stephanie and I were able to show that an equation of this type follows at this order, at order alpha prime cubed. But it was an extremely arduous task and difficult to implement, I think, beyond what we did. But at least it shows the point that this Laplace equation is a consequence of supersymmetry. So I've already mentioned this. One immediate question is, what about all the other terms at the same order in alpha prime? At the moment, there is no efficient way, there's no way at all, actually, of generating all of them. A large subset are known, but by no means all. And it would be very nice to have, I think that understanding how to write down all these terms would by itself tell us a lot about this maximally supersymmetric theory, because the impediment to writing this down is precisely that we don't have an off-shell formalism. And also, there are uses, as we heard yesterday, for high derivative terms at this order in string theory. But I'm going to talk more, so I could give a talk entirely about these other terms at this order, but instead of that I'm talking more about the terms beyond the r to the fourth term, and we don't have many tools for looking for these, but I'm going to talk about the connection between 11-dimensional supergravity and string theory in order to try and deduce something more. And at least up to order d to the sixth r to the fourth, and perhaps beyond, there are statements which seem to be exact statements that one can make about these coefficients, but something new happens at d to the sixth r to the fourth. Yes?
There's something fundamental I don't understand.
Yes.
How should we think of these effective actions? Should we or should we not include
Well, I'm talking about the amplitude.
Sorry?
I'll repeat what I said to Tom, precisely because of your question. I mean, your question is precisely related to the reason I'm talking about the amplitude. I'm using, this is a, the answer is yes.
Should you compute loops with
Yes.
this action or not?
Yes. Or should you compute loops with it?
No, I don't understand. This is just the just read off the amplitude, or should you iterate the terms that you have in order to find the amplitude?
No, I'm just reading this off the amplitude.
So let's start easy, just trees. Should you do trees?
I'll show you how I get this in a minute, okay? Then you'll see it. Okay?
This is the generated function. This one.
So this is not the effective action.
No.
Okay. Should you iterate in trees or not? So if
No.
so this is not any effective action.
So I'm using the language actually just as a shorthand notation for talking about particular terms in. Otherwise, I have to write s cubed, t cubed, u cubed, or whatever in for d to the sixth. So when I say d to the sixth out of the fourth, I mean a term of order s cubed times out of the fourth, or t cubed times out of the fourth. Whatever. What? Of the 4.9. So let me actually, given the time, I don't, and given your knowledge, I don't have to say this. I can say this quite quickly. I'm going to just remind you about the connection between M theory on the two torus and the type 2 theories on the circle, type 2a or type 2b, where the radius of the circle in type 2a is the inverse of the 2b radius, and is related to the.
Sorry, Michael, so I don't want to use the word.
Marty, what time is that? 10:30.
You have
No.
2 more minutes.
Yes.
Don't worry. Should this also be true, this in principle, for higher endpoint functions or not?
Should what be true?
You're using some procedure, which I don't understand. Imagine you computed them all. Would the same thing work also for 5-point functions, 10-point functions, etc., or not?
The procedure would work in principle, because all I'm doing is calculating the amplitude.
Even in 10-dimensional infrared.
Oh, I see. Sorry, okay. Fine, okay.
Endpoint functions are too lazy to compute now. You
Sure.
need infrared with-
No, okay, then you'd have to worry about the infrared.
And then what do you do?
Well, I don't. That's,
Nobody chose it.
I chose a very, very special set of, a very, very special principles. You do what?
There's no physical infrared divergence.
Can we? I'll miss my flight if I don't. Yes.
Why don't we continue this discussion afterwards, please?
I'm going to do something very specific. So, there is a standard connection between 2A and 2B theory on a circle and M theory on a torus, in which the volume of the torus is related to the type 2B radius in this way, and the complex structure of the torus is simply the complex coupling constant. And then in the limit in which you shrink the torus to zero volume, the radius and the 2B theory goes to infinity, and in the limit in which you shrink you expand one direction of the torus, you get the 10-dimensional type 2A theory. That was understood in the classical theory a long time ago. Now, if you now let's look at Feynman diagrams in 11 dimensions on this 2 torus. The simplest case is the simplest non-trivial case is the one-loop Feynman diagram, and as has been known for many, many years, if you add the Feynman diagrams of n equals a supergravity together, then they have a remarkably simple structure. Again, and after the fourth term factors out, and you're left with a scalar field theory box diagram. And this is to be evaluated on a 2 torus, and what you do then, one way of evaluating it is to think of this particle here, going around the loop, winding around the 2 directions of the 2 torus with winding numbers m and n, m hat and n hat. And you then discover that the divergent, this is of course divergent, it's much less divergent than it would have been were there not this prefactor. So an important point, of course, is that there are 8 powers of momentum that are factored out. So this is an 11-dimensional scalar field theory box diagram which has a lambda cubed divergence where lambda is a cutoff. But no, so lambda divergence, even if it's much less than it would have been without this prefactor. When you evaluate this, you discover, not surprisingly perhaps, that the non-zero winding number sectors are finite, completely finite, whilst the divergence, which is a cubic divergence, if you just catalogue in any local way you wish, depends on the volume of the torus linearly. And so there is a volume factor here, while here there's an inverse volume to the half factor on the non-zero winding numbers. So the divergent piece actually goes away in the limit in which you would get the type 2b theory. And you're left with a completely finite expression. And the expression for the amplitude has this form. So it involves this Eisenstein. So the sum over the winding numbers just reproduces this Eisenstein series that was already known to be the prefactor of the R to the fourth term, with a particular power of the volume. But that power of the volume is precisely what you need when you map back from the M theory coordinates to the string theory coordinates in order to give a 10-dimensional limit in the type 2b theory with this R to the fourth Z3 pattern. So now I am translating back to the language of the action, but I could have stuck in the amplitude. And this contains tree-level and genus 1 perturbation theory terms, together with the instantons, and this agrees exactly with what's known in string theory, with the data I showed you. Well, there are 3 bits of data. There's tree-level, there's genus 1, and the instanton action. And although you could arbitrarily change the overall normalization, and you could also shift the dilaton in order to get agreement between tree-level and genus 1, you would then screw up the action, yes?
Yes, so I'm confused because in the type 2b case you compute a 10-dimensional amplitude, right?
Yeah.
But in this case, if you follow the duality, then you miss all the momentum modes in the tensor direction.
I'm sorry, I should have said, by the way, sorry, this is not quite what you asked, but I should have said I'm considering the graviton, the external states, to be polarized and have momentum in the non-compact direction. I'm not sure if that's what. Is that what you're asking? Maybe. But you certainly have to sum up in the internal ones, all the momentum modes. So that was just the expression that you get from the lowest order expansion in powers of S, T, and U. If you now expand to arbitrary order in S, T, and U, you get an infinite series of terms, all of which are finite, because the divergent term is independent of S, T, and U. And it gives an infinite series of higher derivative terms in the 2a limit. The 2b limit, these don't look so nice, but in the 2a limit, it gives a infinite series of terms with powers h, 2h of derivatives, which are correlated with the genus, with the power of e to the phi. So these are terms of genus a half of the power of the derivatives, and they go on forever with coefficients that I haven't written down. But for my arguments I'm going to give later, we have a suspicion, but it's no more than suspicion, that these coefficients are actually exact, meaning that even though I'm only considering one loop supergravity in 11 dimensions, there is an infinite series of coefficients which are determined exactly and don't get contributions from higher loops. So I should back off, of course. I'm talking about doing perturbative calculations in a non-renormalizable theory, so you may be slightly puzzled by that. But I'm picking out particular bits of information here, which appears to be determined exactly. Later on, I'm going to try and generalize that in a much more speculative manner. So, yes.
So what you're saying is that if you choose the external gravitons to be polarized in the non-compact direction, then you can never have anything in the loop.
No, you sum over all the things in loops automatically.
Right.
But it never changes. It's conserved around the loop.
Yeah. So this is what confuses me, because if you follow the duality from M theory, then what corresponds to momentum modes in the tensor direction of type 2b theory is a wrapped membrane on the torus. No,
this is going around the loop. So you can't wrap there aren't enough directions to wrap the membrane in 8 dimensions. You would have wrapped the ward volume. So now let's go to 2 loops. 2 loops has been understood in supergravity in any dimension, was understood by these people in 1998. Again, there's a rather remarkable fact that when you add all the Feynman diagrams of 2 loop supergravity together, you get some prefactor which now involves 4 more derivatives, which I've written as S squared here, times 2 kinds of a planar and a non-planar scalar field theory double box diagram. And again, it's just scalar field theory, so again, you can contemplate evaluating this on a torus, but now you have to wrap. Now there are 2 loops, so you have to wrap both of these field theory loops around the 2 different cycles of the torus. So there are 4 winding numbers. So things look more complicated, but to cut a long story short, let me say that in that way, looking at the leading order in S, Q, and U, you can isolate the d to the fourth out of the fourth term and this function z 5 halves that I mentioned earlier. And again, this agrees, this contains tree level and genus 2, and the coefficients are absolutely determined because this is field theory where the relative one loop and two loop diagrams are uniquely, the relative coefficients are specified, and the absolute coefficients agree with the rest of the tree level and the genus 2 results. The genus 2 one has only recently been evaluated, so that confirms that this function is a correct function. So I'm trying to use the word genus for string theory and loop for supergravity, because I'm getting, from one loop, you already saw that we got an infinite set of terms with higher genus in string theory, so it would be confused. There's a bit of confusion here, possible. Now let me go further. If you expand that two-loop diagram to the next order in SQU, something new happens. This would be the sixth out of the fourth, and the reason for going further is precisely because something new happens. You get a term, a modular function that I've now given two indices to. I've put it E 3 halves, 3 halves, because this satisfies a different kind of equation. It satisfies a Laplace equation now with a source term on the right-hand side, where the source term is quadratic, and it's quadratic in the function that we've seen already came into the R to the fourth term. And this seems to be the beginning of a pattern which persists, I think, as I will say in a few minutes, that as you go to higher orders, you get the... so this E is, again, a modular function satisfying this time a Poisson equation in the moduli space with a particular source term. And if you now extract, and I won't belabor this, extract the piece which is independent of the phase, so this E to the 2... This piece, which depends on the one scalar, is an instantonic piece. This piece is the bit which has zero phase, so the perturbative pieces are in here, and you can equate the powers of the coupling constant, and you can pick out the terms here. Here there are more terms, the tree level, genus 1, genus 2, and a genus 3 term, which is rather subtle to extract, as well as instanton and anti-instanton pairs, which have no overall phase, but which have precisely determined coefficients, which I haven't bothered to write down. And again, the agreement, these to the extent that we can check anything, these agree precisely with what we expect. Tree level and genus 1 agrees. The genus 2 coefficient has not yet been extracted from the string theory. The genus 3 coefficient, of course, has also not been extracted from string theory directly, but rather remarkably, at least when you do these calculations, it seems remarkable, the value of the coefficient in the 2B theory, which is what I'm talking about here, agrees precisely with the d to the sixth term in that infinite series I showed you before, which came from a one-loop calculation. Now, it's known, actually, I guess Berkowitz pointed this out, that up to genus 4, type 2A and type 2B string theory 4-point functions have to be equal. So, well, we didn't know that when we did this calculation, so we were astonished by the agreement. This d to the sixth after the fourth in the 2A theory, remember, came from a one-loop calculation, which was just a simple integral. Extracting this three-loop term from this modular function involved using some rather obscure Ramanujan identities, which look altogether different in nature from the calculation in 2A theory. So that looked good. And then there are these other effects which we don't know much about. So let me just quickly say why this Laplace equation with a source, or the Poisson equation, arises. So for the first time something new has happened. And the new thing that's happened is that at this order, if I try and argue from supersymmetry for such an equation, I would have to consider the classical variation of the new term in the action, S6, that's d to the sixth after the fourth, plus a new supersymmetry transformation of the classical action, but then there's an intermediate term, which would involve the previous new supersymmetry transformation of order alpha prime cube that I mentioned earlier, times acting on the r to the fourth term and its partners, which is also order alpha prime cube. So there's an intermediate variation that comes in, and likewise in the closure of the algebra, you have to take into account the commutators of the intermediate supersymmetry transformations in closing the algebra. And there you can see schematically, although we haven't done this in detail, that, that this mixing with the intermediate thing is what is giving rise to the source term in the Poisson equation. So we'd like to, our ambition is to go further and have some general structure at any order for such Poisson-like equation, and then hopefully see how you get some generating function which goes all of them at once. We certainly haven't done that. However, there is motivation, which I will allude to quickly, for believing that at some general order d to the 2k, that epsilon, the E satisfies, the E is no longer just a modular function, a single modular function, it's a sum of modular functions which satisfy quadratic Laplace equation, Poisson equations with quadratic sources of the sort I've just described. But now there's a degeneracy, there are several modular functions that have to be added together with different coefficients, different eigenvalues, if you like, on the left-hand side and different coefficients on the right-hand side. So it's about, they're coupled equations for these coefficients. One of the reasons for believing this is true is just the schematic supersymmetry argument I gave before, which indicates at least that you can get such a structure and that you always have a quadratic source on the right-hand side. You can also go further in what I've been talking about in a very, very precise way. You can expand the two-loop amplitude I've been talking about to yet higher order, and we've systematized this and we've gone to quite high orders. But one particular term which I just pick out is a term at order d to the 10th after the 4th, or in the amplitude an s to the 5 term, which this is not something that survives in 10-dimensional type 2B theory because it's got 1 over r cubed in it. But nevertheless, it's given by some function, there's some modular function f, which indeed is a sum, in this case, of 5 different functions which each satisfy Laplace equations with sources. There are 2 types of sources, and you can figure out you can actually work out the content of that, the perturbative content with that, and to the extent that we can check anything, which is rather limited here, it agrees with exactly what one would expect. In this case, however, something new happens because now we get logarithms, and these logarithms are the symptom of the fact that when you get up beyond d to the 6th, d to the 8th and thereafter, there are normal logarithmic thresholds in the 10-dimensional theory. So you have s to the 4th log s times, and when you transform that into Einstein frame, you get log omegas coming in. And I won't go into the details, but this is a symptom of that fact. So there's again something new happening. But there's enormously rich content of this. And of course we don't know, since we can't check these things, why they would be exact. Although secretly believe it. So now let me turn to, what time did I start? 10. So this is just saying that we have many such examples. Let me just make a comment. I stopped at 2 loops because when we were doing this, there wasn't a 3 loop. Well, I stopped at 2 loops. Firstly, there wasn't a 3 loop calculation that Burnett et al. Had done, and only Burnett et al. Seemed to be able to do this. And furthermore, if there had been one, it would have been too complicated for me personally to have analysed. But now there is one, because recently these people, whose names I should get right, but I won't, Byrne, Kosover, Dixon, Royban, and a student, I think. Unfortunately, it should be called the student et al., have actually figured out the 3-loop terms, and they've found that at 3 loops there's yet again another factor. Remember, going from 1 loop to 2 loops, there was an overall factor. This is very important in what follows. There was an overall factor of s squared. In going from 2 loops to 3 loops, they found another factor of s. This is something we've actually conjectured, because in order for these d to the 6th after the 4th and d to the 4th after the 4th terms to be protected, in other words, to explain why we got what looked like exact answers, it had better be true that they can't be contaminated from the 3 loop or higher loop terms, and so we expected that there would be an extra factor of s. And in fact, they found it rather recently. So in principle, one could try and evaluate that on a tutorial. So let me now turn to a much more speculative kind. So everything I've said so far has been at least in some sense precise, and the precise formative. Here I'm going to be much more speculative and ask whether we can say anything about the general structure beyond 2 loops, beyond 3 loops. By asking for string dualities to play an important role, in other words, by assuming string dualities. Now here, I'm not saying that perturbative supergravity is N theory. Of course I'm not. It's a non-renormalizable theory, but the philosophy is it's a non-renormalizable theory, and therefore there are arbitrary numbers counter terms with unknown coefficients, more and more in every order, which hide the short distance structure of the theory. But the question is, can one nevertheless make sort of structural comments about it if one assumes that one wants to reproduce string theory when you compactify on a torus or on a circle? Let me just do the circle case here. So I'm considering an L-loop contribution to string theory on a circle, and it will be divergent, and it will diverge with some power of a cutoff, and the power is related to the number of derivatives in the term I'm looking for. So I'm looking for a particular term. Sorry, I'm saying this wrong. This is a L-loop term, and in L-loops there is a overall factor of some power derivative times r to the fourth that comes outside of the action, of the amplitude, or the action. What we know about this is that at one loop, you just get r to the fourth, that's what I told you before. At two loops, you get b to the fourth r to the fourth, that's what I told you before. And now, with the new results, we know at three loops, there's a misprint. Sorry, this should say three. At three loops, there is a d to the sixth r to the fourth outside the amplitude. Nobody knows whether this continues, so let me not assume it does. Let me just assume that, I'll assume what is commonly thought to be true, that once you get a certain power factoring out, then at higher loops you never get a smaller power. So these powers, the low powers are protected. So at higher loops, I'm going to take beta to be bigger than 3. Actually, I think I've written transparency where I've kept this at 2, because there's no transparency. But that's the sort of primitive divergence of the diagram. There could be subdivergences, which this is the worst divergence you can have. You could have terms which have subdivergences or which are finite, and you can expand this in a power series in S, T, and U. This is I'm talking about the amplitude here. I'm writing it as if it's an action, but I'm thinking of it as an amplitude, which I expand in powers of S, T, and U, which means higher powers of D squared in the action, but D squared always comes with R11 squared, and so you get powers of R11 squared D squared raised to the power of V, and so the extra derivatives. This is exactly what I've been talking about in the examples. The reason for going through those examples was to illustrate in simple cases exactly this pattern, that there are high power of S, T, and U multiplying the original derivatives on r to the fourth. Now I can translate that. So I've got these parameters, W, which indicates how divergent, whether I'm talking about subdivergence or whatever, power V, power beta L, and I can translate that expression into the 2A string variables by using the dictionary that I reviewed earlier, where, so R11 cubed is related to the coupling constant G squared in string theory, and the metrics are related in this way. And then you find a term, the term I mentioned before, corresponds to a term with some power d to the power 2k r to the fourth, where k is related to the variables I had before in this way, and e to the 2h minus 1 phi, this is a genus h term in string theory, where h is related to the variables I had before in this way. So there's some translation. But you see from this expression that W, I should have said W is positive, so h is bounded. Now I'm going to assume that h is an integer. Since I'm talking in generality about an expression that I can't evaluate, then I don't know why h should turn out to be an integer. However, in all the cases that we did, which were in some sense simple, h was an integer, and furthermore I'm going to assume h is bounded by 0, because if it corresponds to string theory, it had better be both an integer and non-negative. So this expression here leads to a very strong bound. It says that h is always less than k. So the genus is always less than the half the derivative. But that's true when n is bigger than 1. L equals 1 is special, because when L equals 1, the fact that beta L is 0 actually allows the one-loop case that I mentioned earlier. So earlier, I did a one-loop case explicitly, and I showed an infinite series of terms, and those were the terms where h was equal to k. And this is what I meant when I said that we can't see any way in which higher loops can change the L loop the H loop terms, the d to the 2k r to the 4th. So to summarize, what we think is true, but this is, of course, there are lots of assumptions that have gone into this, is that, that d to the 2k r to the 4th is not renormalized beyond genus H in 2A string theory. This agrees, by the way, with some rather recent work by Berkowitz up to k equals 5. Now, Berkowitz was using supersymmetry, or his version of supersymmetry, his pure spinor formalism. So his results are much more solid. But up to 5 loops, Berkowitz also finds that the powers of D that come outside the string theory amplitude. So he looks at string theory, of course. He's doing string perturbation theory. And at low energies, the low energy limit in 10 dimensions of string theory, he points out, has a d to the 2k r to the 4th outside it, at least up to k equals 5. At k equals 5, beyond k equals 5, the formalism he uses breaks down. So nothing is known in his formalism beyond k equals 5. And then the second comment is that we believe that the H equals k term is given exactly by the one loop calculation. Well, so now let me get even more speculative and make even more, well, I'm not sure how to say this. If what I'm saying has anything to do with finiteness, or possible finiteness of n equals 8 supergravity, then the argument will go roughly as follows. If it hasn't, then the argument that follows is incorrect. So what we found is, we found that for a given power of derivatives, there is a non-renormalization theorem that there are no contributions beyond k loops. Turning that around, what this says is if you take a H loop amplitude, which in terms of the effective action, so, yeah, again, this formula isn't quite, let me talk in terms of the amplitude, since people have been worried about the distinction. What this is meant to say is that you take a genus H contribution in string theory and look at the low energy limit. The low energy limit begins with S to the H, or D to the 2H, R to the 4th, plus higher order terms. So the leading term in the low energy limit, and this is the important point, the leading term in the low energy limit in string theory, and this has been shown explicitly, as I say, up to 5 loops, but we believe may hold beyond 5 loops, up for all loops, is that there is a D squared for every time you increase the genus by 1, you get an extra factor of S, T, or U. This is the rule which I was talking about earlier. But that means that if you go back to the supergravity analysis, and the supergravity analysis of Bernotal applies in any dimension, because what they're doing is adding Feynman diagrams before they do the loop integrals, and they're finding that these factors factor outside the amplitude. So if you believe that this factor will also factor outside the amplitude of the supergravity amplitude, because it's the low energy limit.
Mike,
yes.
You have any hint whether they do appear or have zero coefficient?
If they have zero coefficient, that's fine.
Give us an example.
Then it'll be even higher. I mean, the key thing is that at least...
You gave us an example which some of them are missing, right?
Yeah, but so it doesn't matter if they don't appear. The question is, which is the first one? Is at least D to the 2A? That's the issue. Because the point is that if you pull out enough factors outside a loop amplitude, then you lower the divergent amplitude. It's straightforward. So what this means is there are subtle cancellations between the loops, and this is what's happening at 3 loops, for example. Different Feynman diagrams, which appear to be unrelated to each other, actually, have divergences that cancel. And so that they're much more convergent. And indeed, so if this were to work, if this were to be true, then one would find that at genus H, if I go back to a previous formula I had, then now in 10 dimensions, because I'm talking about the low energy limit of string theory and comparing it to 10-dimensional supergravity, which is of course a non-renormalizable theory, but nevertheless, the divergences of that theory in 10 dimensions would behave like lambda to the 6h minus 6, which is much better than it would have been were there not these factors of D squared out front. Now, if I assume that these factors out front are there in front of the Feynman diagrams in any dimension, as they are up to 3 loops, then I can think of the d-dimensional reduction of the procedure. And then that formula I just had, where d was 10, when d is 10, I can get the formula I just had, but in d less than 10, you get this formula here. The degree of divergence is much reduced from the naive degree of divergence in any dimension because of these three factors, and you see that something special happens when d is 4. But this formula is only true for h bigger than 1. H equals 1 is always special. So if, and this is a big if, so it's another assumption, if you can take the low energy limit and compactify at the same time, then the condition that there are no ultraviolet divergences is the condition that this exponent here should be less than 0. If it's equal to 0, there could be logarithms. But, so the condition of ultraviolet divergences is that for at any genus H, it's free of ultraviolet divergences when the dimension is less than 4 plus 6 over H. And as you can see, this is finite then for the first time as you come down in dimensions, precisely in 4 dimensions, for all genus. This is in fact the same formula. So this maybe should probably be much bigger. As time goes by, I make this maybe bigger and bigger and bigger. Because I'm not entirely convinced by the argument. This is the nature of the argument.
Why? Why do you make it bigger?
Just because there are lots of different assumptions that come in. Much more strident conjectures are made by Byrne et al., who are doing direct calculations of multiple amplitudes. And they have claims which I don't fully understand about patterns they see at all orders in perturbation theory, which they claim is an indication of finiteness. But the actual concrete calculations are up to phi loops. Going to phi loops is useless, it seems. Well, going to phi loops has to be done by somebody. But then you have to go to 4 and 5 and 6 and 7. And the miracle, I think, would appear if it was finite. In the way I'm talking now, there would be a miracle if it was finite in more than 9 loops or more. Because I think one can argue using Berkowitz's results already that it should be finite up to 9 loops. But this condition is the same as for maximally supersymmetric Yang-Mills, which is, of course, the tantalizing figure. The reason why I'm talking about this, even though I'm not sure in the end whether this will be correct, is that this condition is tantalizing because it's the same condition as n equals 4 Yang-Mills. Of course, in n equals 4 Yang-Mills, we have a theory which is renormalizable. Yang-Mills theory is renormalizable in the first place, so making it finite is rather a small step. And furthermore, it's a conformal theory, which is very special, whereas the theory we're talking about now is not. Anyway, whether or not one believes that this is perturbatively finite, there is an altogether, well, what sounds like a different question, although it may be related, which is, does it make any sense to talk about n equals 8 supergravity as a theory in its own right, decoupled from the superstring? In other words, even if you define a perturbatively finite series, the series may be meaningless for other reasons, which I'm going to talk about. So I recently wrote a paper with John Schwartz.
Your argument was sort of assumed it could be decoupled.
Yes, that was the assumption. I agree. Yes, yeah. So now forget the 4-point function and just forget what I've been talking about for a moment, and just imagine compactifying string theory on a torus to some arbitrary dimension d, and asking that in that dimension the extra states of string theory decouple in order to leave the supergravity theory in that dimension. So what you want is, in particular, you want the fundamental string states to become infinitely massive, and the Kapitza-Klein modes and the winding modes. You want them all to be big compared to the Planck mass in d dimensions. And that corresponds to these conditions, that the string distance scale, R is the sort of common radius for all dimensions. I'm talking about the simplicity about having equal radii on a torus. This would make the Kapitza-Klein modes massive, and this would make the winding modes massive. But in addition, in string theory, and this is of course the point, this is a rather elementary point, there are of course many other states. They are in fact, in some sense, well, the Neville-Schwartz 5-brane is the magnetic dual of the winding mode, and the Kapitza-Klein monopole is the magnetic dual of the Kapitza-Klein charge, and then there are of course all the V-branes. And you have to worry about what happens to their masses. Now, what we're talking about is comparing with what happens in supergravity, where you do a perturbation expansion in d dimensions, with a fixed Newton constant. So you want to fix Newton's constant, or the d-dimensional Planck length, whilst you take this limit. I'm sorry, there's something's gone wrong with this, with my animation. So you can ask what happens if you fix LD, what happens to the matter of these states? And as you can see, if you insist that the Kaluza-Klein modes and the winding modes became infinitely massive, and the string modes became infinitely massive, then the that 5 grains in the Kaluza-Klein monopoles associated with the duals of the Kaluza-Klein charges, they all become massive. And some of the D-branes become massive. Well, it depends which P you choose. The phi brane has a finite mass, but then, depending on P, some of them become massive. Good. I won't need it, I think. So it seems that starting from string theory, it's not possible to take a limit which gives pure supergravity with just the supergravity states, in the sense that supergravity people mean, which is to hold L4 fixed. So I've been talking about d dimensions. But these formulae, so these formulae are the formulae for 4 dimensions. Similar formulae hold in more than 4 dimensions. And so it seems that in 4 or more dimensions you cannot decouple supergravity from the string. In 3 dimensions, a dimension that Tom doesn't want me to consider, things are different. Because there you can take, there in this limit, all the states become massive. Although there are instantons, which in a sense become massive, so they get zero action. And those instantons will provide large collections to the convection. And the same is true for 2 dimensions, but there the instantons are not massless, but they have, some of them have large actions and some have small actions in the small d limit. So it seems likely that you can define some 2-dimensional, 3-dimensional theory, which is, in some sense, quantum supergravity, but you can't define quantum supergravity. So from this perspective, you can't define quantum supergravity in higher dimensions. And then there are some generalizations which we haven't really fully worked out, which it seems to all work through if you compactify on Calabi-Yau's. You could then ask the question, this is my last slide, you could ask the question in reverse. And I haven't really understood this, the logic of this completely, but if you cannot decouple supergravity from string theory, then it would seem quite natural that there should be some signal already in supergravity that it can't be decoupled from something else. Now, whether or not there are ultraviolet divergences, there are infinite towers of BPS black holes. And if you assume, at least, that in the quantum theory, the duality symmetries that we know about hold, then these towers have to fill out multiplets of E77, and they will correspond to the states I've been talking about, the extra states, BPS states, in the string theory. And from my understanding is that they are likely to produce extra dimensions in much the same way as the D0 branes do in 10-dimensional string theory, that produce the 11th dimension. So I think there should be a signal from the BPS states of the supergravity already that there are extra dimensions and therefore a problem for the theory. And that particular statement sounds like it's true whether or not the theory is ultraviolet finite. However, our original motivation, my motivation with John Schwartz and Hiroshi Oguri was actually to do something more ambitious, which we haven't done, but which would be, of course, very nice, which would be to, assuming the standard law that there are divergences in any case supergravity, then we wanted to try and explain the presence of these divergences in some sense by the fact that there are also massless states in this limit, non-perturbative states, and somehow the combination that these would also give rise to singularities which would cancel the divergences. But we certainly did not do that. I will stop there. Thank you.
Any other questions, comments? Michael?
Yeah.
I would be very grateful if you would clarify something about the argument, which I really didn't understand. So there are 3 kinds of loops in this argument. There's the perturbative loop, there's a genus there too. Is there a relation among these genuses which is clear? Because in particular for the string and the perturbation theory, they were mixed in awareness. And they seem to be mixed in awareness.
I agree with what you're saying, and I don't know of a sensible way of understanding the relationship between those things. I don't. I mean, the occurrence of these particular Poisson equations is something which just came out without any intuition. Well, the intuition, A plus 2 order, there was some intuition, but it wasn't based on thinking of this pinching that it wasn't. But there should be something.
The genus there is not in one-to-one correspondence with the string genus. Or is it? Did I miss that?
Oh, sorry, the genus. What do you call it?
The genus of the modular forms and the string genus were not the same. The modular forms were.
No, the modular forms contain information about many different string genera.
Right.
That's true. And then the modular form came out of a particular genus, a loop amplitude in Supergravity. So there is a correspondence between the modular form and the genus in the Supergravity. But the structure of the equation is the same for all. This structure, you're talking about the structure of the equation with a chromatic term on the right-hand side. Is that right?
Somehow it could happen that the two-loop perturbative computation, the two-loop string computation, gave the same answer, and that contained this two-loop modular form. Then that would be very clear. But that's definitely not what's happening.
No.
And I wonder if you understand what the system is.
I don't, but furthermore, I worked on some very general equations which were conjectural equations. But those, I most definitely do not expect that the pattern, that the exact correspondence with the string theory example will continue simply by doing supergravity calculations. So at some point, I changed tack, and I made general statements. And so we have a general conjecture about the structure of these equations, but we don't know how to calculate the coefficients of these equations in general. It's only for a very simple case. But I don't know the answer to the question.
Could you perhaps clarify the physical interpretation of this four-point function in the following respect? Think about the two-graviton scatter. As far as I understand, you compute any given order of this word just certain terms of the amplitude for this scatter. Question one, is that correct? That's not correct.
Well, we're looking at the derivative expansion, the power series expansion, or the expansion in ST and U.
Right. So you're expanding in ST and U.
Yeah. So we're not capturing a lot of the physics of high energy.
Okay. So these are my questions. First, are the terms that you are able to compute leading in some sense? And the second question, suppose we expect the collision of two gravitons to create black holes, or in any case, get many more than just two gravitons outcome. Does that show in some way?
No, not if you calculate 2 to 2 amplitude, then you only see the 2 to 2. Well, I guess in unitarity, eventually, if you really understood the four-point function exactly, then I guess you would understand a lot more. But
Are the terms that you compute
but if you, sorry, we're expanding. We're looking at the derivative expansion, and we're losing a huge amount of information. I don't think, for example, black hole creation and evaporation.
But I think part of Barak's question was you are computing just one particular tensor structure in the amplitude. You're not computing the full derivative expansion of the full 2 to 2 graviton scattering amplitude, right?
Right.
Okay. So.
No, that's not right. No.
But let's see, at some order in the expansion, should we find some divergence? I mean, infrared. I mean, the action should become non-local at some order.
Oh, so the action becomes non-local. That's what. Yeah,
and not expandable anymore. Yes.
You have
because of massless particles in the loop.
Right.
That should also, and that would be a signature that maybe you have to add production of stuff and so on.
Well, you got threshold. You're talking about threshold.
infrared problem.
You're talking about threshold.
Yeah, I mean, if you have a multi-loop particle, or I mean, in some order, in any number of dimensions, at some order, you will find some infrared problem.
No, but this is already true.
Low order, that you should be able to, that you would have a lot more syncretic problem with just creation of low energy matter problems.
So that's why you would not be able to stop at 4.5. I guess. At some point.
Higher order.
So is there any procedure that's known for defining an S matrix out of all of this?
I thought that in gravity the Bloch-North procedure worked just the way it did.
But it doesn't give an amplitude. It gives a probability.
Right.
So,
Okay.
first of all, this problem only exists in 4 dimensions. A lot of what you were talking about is above 4 dimensions, so it's not there.
Well, almost
But
everything.
there is a paper by Fadeev and Kulish, which claims for ordinary gravity to define real amplitudes of multi-particles, incoming and outgoing states.
Right.
Coherent states.
In 4 dimensions.
In 4 dimensions. Okay. Nobody has ever followed up on that in string theory, to my knowledge, and tried to define an analogous object in string theory.
So you're talking about compactifying string theory.
To compactify string theory to 4 dimensions, just interpolation theory, define the Fadeev-Kulish aspect or analog of it, and see that it's actually influenced.
I'm not even sure this is a string theory question. This is just whether the gravity question.
Well, I think we'd better terminate the discussion. Thanks again, Mike.